My name is Ramakrishna Ambati. I'm working in Visby Medical as a solution architect. Today, I'm going to present a reactive to predictive transforming medical device reliability through secure IoT architecture. Okay, so the traditional approach is whenever healthcare organization typically responds to the medical devices failure after they occur any medical failures that is leading to the downtime and the delayed diagnostics and increase the operational cost. So this reactive paradigm creates a inefficiency in the resource allocation and impacts the patient's care delivery. So our vision is a data-driven predictive maintenance. So that means the reactive system will fix that any medical device failures whenever it is fails, then we'll apply the fix and also it's a schedule maintenance. Whereas our reactive process, predictive processes is a data-driven intervention and also automated optimization. So that means we're transforming the reactive responses to proactive. So through IoT-enabled strategies and anticipate failures before they impact on clinical operations. The secure IoT architecture foundation is completed in three components. One is cloud platform, and so here we are using a very zero trust security principles. We are using MQTT and HTTP protocols. So these two protocols you will use the transfer the data from medical devices to the cloud computing. So then once we transfer the data, then we do the edge computing. That means we'll apply the local pre-processing to reduce the transmission volumes while detecting a critical anomalies. And third one is HIPAA compliance. So that means this is a mutual transport layer security authentication with certificate rotation and real-time revocations. So that pipeline of architecture is in five steps. One is the device telemetry. That means we're continuously monitoring the operational parameters from the diagnostics devices and local analysis and filtering to identify the critical patterns and anomalies in that the edge processing. And we securely transfer the data from transfer to the from medical devices to the cloud computing infrastructure using a security protocol that is HTTPS and MQTT protocols, and we'll store that in the time series. So then we will optimize the database for the telemetry data and advanced analysis for further processing. And finally, analytics engine. So where we develop the machine learning models to generate predictive insights and maintenance recommendations. So the zero trust implementation is a mutual TLS authentication for all device communications. So certificate rotation schedules with the automated management. So that means we will automatically roll out the certifications on schedule basis for the each medical device. And real-time revocations. That means for the any compromised credentials. So that means if you feel like if you suspect anything which is not working, then we will revoke the security certifications and in real-time revocations capabilities. And last one is we also do the audit trailing for the compliance reporting. So whenever you make any changes on the medical devices, and we do have a documentation for the further documentation for the audit trails for the further processing and reporting. So the machine learning development is the feature engineering. So that means we'll transform the raw telemetry data into meaningful predictive indicators using a signal processing, statistical analysis, and domain-specific knowledge integration. And also we have a class imbalance handling. So address the unique challenge of rare failures events in a medical device data sets through specialized sampling and weighing techniques and explainable predictions. So we'll develop the interpretable models that meets regulatory requirements for software as a medical device into a controlled healthcare environment. Continuous learning, so that incorporate the technicians' feedbacks and adapt to evolving device behavior patterns for further improved prediction accuracy over the time. So the feature engine process is the signal processing. So we'll extract the meaningful patterns from raw sensor data through a frequency analysis filtering and transformation techniques. And statistical analysis is a drive key matrix including trends, variance, and correlation patterns that indicate device health status, and domain knowledge that is integrate a clinical and engineering expertise to identify the features which proven diagnostic significances. So the main key improvements are optimize the resource allocation through predictive analysis. So based on the analysis, and we can optimize the resource allocation for the fixes. And automatic ticketing system integrates a maintenance and workflows, streamlines the maintenance of the workflows. So whenever device failures occurs, our workflows will trigger to create the automated of the ticketing system. And also we develop the real-time dashboards. So visualizations enable the data-driven decision making. So that means we can predict at the based on the data visualizations. And so we develop the reports and dashboards. The stake enhance the stakeholder communication across the clinical and technical teams. So that is the major key improvements with benefits of this solution. Okay. So regulatory compliance framework. So we also have a FDA requirements. So address software as a medical device regulations with the comprehensive validation and verification protocols. Audit trails maintain a complete documentation of all the system activities, predictions, and maintenance actions for the compliance reporting. And we also have a quality management. So we'll integrate with the existing quality management system framework to ensure continuous compliances and traceability. So we implement the workflow in the 5 steps. One is the assessment. In this section, what we'll do is we'll evaluate the existing infrastructures and identify the critical devices for the IoT integration. And the second bit is architecture design. So we'll develop the secure IoT architecture with the HIPAA compliances and the zero trust principles. Okay. So then pilot development, we deploy the edge computing units and establish a secure data pipelines for the initial device fleet. So that means we'll roll out this initially only for the 1,000 devices, and not for the, we don't roll out for the major clinicals and hospitals. And then once we roll out the solution, then our model training will collect the telemetry data and develop a predictive models with the validation protocols and scale and optimize, expand to full device fleet and implement continuous learning mechanisms. So the future innovations and research directions is embedded diagnostics. So MEME sensors, which resides in the medical devices. So that sensors integrate directly into the device for enhanced monitoring capabilities and real-time health assessment. Okay, based on that MEME sensor data, we will do the assessments for each medical device. And federated learning. So privacy preserving analytics across distributed device fleets without centralizing sensitive data. And digital twin technologies. So we develop the simulation based on the maintenance planning using a virtual replicas for the scenario testing and optimization. So we have some simulators, it's exactly a medical device. So where we can use for testing, and we can capture all the test scenarios, and also you can use for the training purposes. And the success factor says the stakeholder engagement across the clinical, technical, and administrative teams. Okay. Comprehensive training programs for maintenance, personnel, and clinicians. The clear communication of benefits and measurable outcomes. Phased rollout implementation approach to minimum disruption. Okay. So continuous feedback loops to refine predictive models and workflows. Okay. These are the major success factors with our solution. Key takeaways for implementation is security first. So we'll establish the robust zero trust architecture with the HIPAA compliances before collecting any adjacent data from medical devices. Start small, scale smart. So begin with a pilot deployment. As I mentioned, we roll out for the small and local hospitals like hundreds and thousands on critical devices to validate the models and demonstrate value before enterprise rollout. So then we can test so before rolling out, so we'll demonstrate on the local clinicals. Embrace continuous learning, that is the third one. So every year we build a feedback mechanisms that incorporate technicians' expertise and adopt models to evolving device behavior patterns. Okay. And last one is focus on operational integrations, ensure predictive insights translate into actionable workflows through automated ticketing and decision support systems. So as I mentioned, whenever device failure occurs, our workflows will trigger an automated ticketing system and will give the two solution based on the model what we developed. So our models will trigger and identify the predictive solution to the technicians for the device fix. So that is the end of my presentations. If you have any questions, feel free to ask here. And thank you so much for giving me the opportunity.